Hello, everybody. So in this section, we're talking about the electrons that orbits around an atom, or the nucleus, sorry. Um, so we can imagine a circular orbit of the electron around a certain point, which will be the nucleus of the atom, with a radius capital R. So now the electron itself doesn't is not current because it's just one electron, but we can imagine it as a current since it moves extremely fast in uh, always a small state. We can imagine this to be a tunnel, pretty much, and that the electron is passing through it. Now, unless we look at such a small time that the electrons are not there, the electron will pretty much always be in there. So it will be moving in there. So we'll always have a current. So we can say the current is equals to, like I said, charge over the period. Now the charge is equals to E for the electron, and the period is equals to 2 pi r. Um, well, sorry, 2 pi r over v. My bad. Uh, so we can just simply do the v over here and write it on top. Now the momentum, the magnetic momentum, is equals to I pi r squared. Now we have I from this one over here, and we can substitute it on the left. So we're gonna get EV pi r squared over 2 pi r. And we can solve the pi and the r, we can simplify the pi and the r at the bottom, and we see that we get EV over 2r. Now, the book adds a negative because the electron has a negative charge, of course, and the magnetic dipole moment will be along the z direction. If we imagine that we have the z direction pointing up on our um, on our yeah, image. Okay, sorry, actually pointing down because it's a negative. All right. So, but with this, we could find the torque. I'll write it as actually the torque. I'll write it as tau, and we know the torque is from what we proved in the previous videos is equals to. Let me find it. Oops. Okay, m cross b. So it would be equals to m cross b. Okay. So now the electrons is slows down is affected by different forces, first of all, by the electric force and by the magnetic force. So let's start with the electric force. Using electric force, we know that the formula is equals to 1 over 4 pi epsilon naught, and then the charge of the electrons times the charge of the electron, which actually we know it's the same charge. So we can just say the charge is equals to E times E, or E squared, over the distance squared, which will be r squared because the orbit has radius r. Okay, and is equals to the centripetal force, which is equals to the mass of the electron times the velocity squared over the radius squared. Now, when we add the magnetic force, so Fb, we know that is equals to the charge of the electron, which actually will be negative charge, times V cross B. So let's add this in our formula, and we get that the left side adds one element that is equals to, oops, let me check on my microphone, yes, okay. It happened before, I don't want to do it again. So minus, or minus minus, plus E times V cross B. Now, of course, is equal to the mass of the electrons times the velocity squared over the radius squared. Now, the cross product, it will be equals to V times B times sine of theta. So in order to make things easier, the book says, imagine that the angle theta is equals to 90. So this part here can be said is equals to 1. Okay? So we get the left side to be equals to, let me just copy this over here, and then VB is equals to mass of the electron times the velocity squared over the radius squared. Okay. Now, of course, this velocity will not be the same as just with the electrons. So this velocity that we have will be called V bar, something like this. And we can rearrange our equation because we know that this part over here, the set is equals to me over v squared over r squared. So if we bring it to the left side, if we bring this to the left side and do minus, it's like doing minus of this part over here. So let's just rewrite this instead. So this over here. Let me just cancel it out. Wow. Okay. Of course, we brought it to the left side so we can get rid of it from the right. We brought it to the right side so we can get rid of it from the left. And we can write this as EVB. Oh, sorry. This one, of course, changes to V line is equals to, well, we can factor out the ME over R squared is equals to the V line squared minus V squared. Or if you remember the product rules, ME over R squared, actually something very different algebra, so equals to V line plus V times V line minus V. Now let's say that this value right here, delta V, is very small. So it's approximately 0. Approximately, we don't want it to be 0 in our case. But so here we can say that we have the same value, right? Because if we say that the difference is almost nothing, we can say that these ones are pretty much the same. So we just call it 2V line, just to make things easier. So on the left side now we have EV line B times ME over R squared times 2V line times delta V. And now we can simplify this V line with this 2. Actually, sorry, let me just do a little bit easier. This V line, yeah, with this V line. And then we get that delta V is equals to EB. Oh, did I not simplify the R squared there? Oh, that's my bad. I've been writing this wrong on the left side the whole time. This is not R squared, no, just R. That was my bad from the beginning. Okay, so of course here again, EBR over ME, and then 2. I'll put it in front. So this is our delta V. So now we can find the change in the magnetic moment, which we said was equals to, let's go back and find it. Where is it? There it is, right here. This was our magnetic moment. So now instead of V, we have to find the delta M, so we're going to use delta V. So negative E over 2 times delta V times R in the Z hat direction. Or we can rewrite this as negative E squared R squared over 4M E times B. If we just go back and plug in this value for delta V, because they're the same thing. Now, one thing that you have to look at it is that our change momentum is negative our magnetic field. Well, this one is, of course, mathematically, and we can also see it in our change. But anyway, this is pretty much all that you need to see in this section. The calculations are straightforward. They're straightforward. Um, as you can see, I made the mistake of saying that it was equals to the me over v squared r squared, but apart from that, everything else was correct. And as you can see, we started from a current, or what we suppose is a current, because of course we know that the electron will not stay uh, in this space the whole time, but we know it's going to be in there for most of the time we look at it, so we can just think of it as a current. And if we imagine the whole thing around, we can think of it as a current, even better, the whole orbit. And we end up having that the magnetic moment is equals to the charge of the electron, negative charge of the electron, times the radius squared over 4 times the mass of the electron times the magnetic field.